Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today we are going to discuss the synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. Dear student, we have studied so far some of the important aspects of synthesis and design of inorganic materials, in which we have already studied some important techniques to synthesize inorganic compounds, especially hydrothermal synthesis and sol gel synthesis, as well as high temperature synthesis, while chemidos methods. Moreover, in the last lecture, we discussed about the synthesis of BiFeO3 by chemidos method. It is a quite difficult synthesis which would be easy if we synthesize it at about 800 degrees Celsius. And we have discussed the synthesis of BiFeO3 in detail by even sol gel methods. Molten salt synthesis is also an important technique to synthesize some of the important inorganic organic hybrid materials and the pure inorganic materials. Now the third one is the gas phase methods. In gas phase methods, we people are going to discuss and learn about some of the important gas phase methods. The first one is vapor phase transport. The essential feature of this method is the formation of a volatile, unstable intermediate that contains at least one of the elements in the desired final product. The method, which is the vapor phase transport method, may be used to synthesize new compounds, to grow single crystals, or to purify a compound. Actually, the synthesis of new compounds and growth of the single crystals of that new compound is quite helpful for the better characterization and for the better understanding of the properties of any new synthesized compound. It involves chemical transport along a temperature gradient via vapor phase. The method consists of a tube, usually of silica glass, with reactants A at one end, which is sealed under vacuum, or with a small amount of the transporting agent B. The method, it is actually the method which is shown in this diagram A, that it actually consists of a tube. It usually made up of silica glass, with the both of the reactants, which is reactant A at one end, and the end is actually sealed either under vacuum or with small amount of transporting agent B. This is actually shown in this A diagram. The tube is placed in a furnace such that a temperature gradient of about 550 to 100 degrees Celsius exists inside the tube. In the simplest case, A and B react to form gaseous intermediate AB, which permeates the whole tube and decompose somewhere in the tube. This actually the it is thought to be the simplest case to that in which one A and B actually react to form gaseous intermediate AB. We can say this is the AB gaseous intermediate, which actually permeates the whole tube and decomposes somewhere in the tube at either higher or lower temperature to redeposit A, and it is actually shown in this B diagram. The method depends on the existence of reversible equilibrium between A and B and AB, in which A and B is actually reacting with each other in a closed tube at about 50 to 100 degrees Celsius, and it may permeates the whole tube and decompose somewhere in the tube at either higher or lower temperature to redeposit A. The method depends on the existence of reversible equilibrium between A, B and AB. The equilibrium constant K should be small. If K, which is actually small, is 0, then no AB would form and vapor phase transport could not occur. If K is very large, then AB would be stable and would not subsequently decompose. So what we have learned that if the value of K is quite large, then this AB would be stable and would not be decomposed. If formation of AB is endothermic, then what happened? If it is formation of AB is endothermic, then it forms at higher temperatures and decomposes at lower temperatures. It means that equilibrium is displaced to the right with increasing temperature and to the left with decreasing temperature. So it should be very clear and understandable, and we people should have to remember this point that equilibrium is displaced to the right with increasing temperature and equilibrium displaced to the left with decreasing temperature. The exact the exact opposite happens if AB, this is the actually AB, if this AB is, if this AB forms exothermically. So it is quite easy to understand. Hence the tube is arranged for reactants A to be either at either the hot end or cold end respectively. Since K is temperature dependent, a concentration gradient of gaseous AB builds up along the length of the tube, which actually provides the driving force for gaseous diffusion and therefore for chemical transport. An example of an endothermic reaction which can be used for chemical transport is the formation of gaseous platinum oxide PtO2 at about 1200 degrees Celsius, or sometime we need to provide temperature which greater than 1200 degree Celsius. In We can see in this equation that platinum is in solid state, which is reacted with the oxygen and subsequently changed into platinum oxide P2 PtO2, which is actually a gaseous state. And this reaction occurs at about 1200 degrees Celsius or even more than 1200 degrees Celsius. The platinum oxide P2 PtO2 diffuses to uh, lower side. PtO2 diffuses to lower temperatures where it may deposit well formed crystals of platinum metal. In furnaces that contain heating elements of platinum, it is common to find platinum crystal deposits on cooler parts of the furnace wall. These form a, these forms form by a process of vapor phase transport. A nice but it's quite expensive example is actually shown in this C part, which is the part of ceramic tube in which a platinum element coil had transported to the tube surface and deposited as single crystals of platinum. We people are well aware with the prices of the platinum, which is very high, and sometimes it is believed that the prices of platinum is equivalent to prices of the gold. So this is although a good example, but it seems to be quite expensive. The Van Arkel method for the purification of certain metals makes us an exothermic reaction between the metal and iodine to form a gaseous iodide. For example, we should took the example of chromium metal, and it is reacted with the iodine, and it is the exothermic reaction in which chromium iodide is formed. Since formation of chromium iodide is exothermic in nature, chromium metal is redeposited at higher temperature. This is actually the exothermic reaction in which chromium and iodine is reacted and form chromium iodide gaseous molecule. Chromium metal is redeposited at higher temperature due to its exothermic nature reaction. Other metals which may be purified by this method include titanium, hafnium, vanadium, neodymium, copper, titanium, iron, and sometimes thallium compound metals. By this method, the metals may be extracted from their carbides. Uh, we make use nitrides and even oxides for the purification of metals. The Mond process for the purification of nickel involves an exothermic reaction of nickel with carbonyl to form gaseous nickel carbonyl. In this reaction, we can see that nickel and with four molecules of carbonyl are reacted at elevated temperatures and change into nickel carbonyl gaseous molecule. This is actually an old industrial process for extracting high purity nickel from impure nickel obtained by reduction of nickel oxide, but is falling out of favor because the environmental issues concerning nickel contamination and also human health concerns over the high toxicity of carbonyl and even nickel carbonyl. So this is a good example of CVD, chemical vapor deposition. After nickel carbonyl, an elegant variation to transport two substances in opposite directions along a temperature gradient is possible. If it is possible if one reaction is exothermic in nature and the other one is endothermic. For example, tungsten oxide and tungsten may be separated by using iodine and water as gas phase. Actually, tungsten is deposited at 1000 degrees Celsius and tungsten oxide at about 800 degrees Celsius. The reaction involved are in which tungsten oxide, which is in solid state, is reacted with gaseous iodine and change into tungsten oxide iodide, which is actually a gaseous compound, in which tungsten is actually deposited at 1000 degrees Celsius while tungsten oxide at about 800 degrees Celsius, and tungsten solid may reacted with the water and iodide in gaseous or vapor state at 1000 degrees Celsius and as well as 800 degrees Celsius, in which we can see that it is changed into tungsten iodide and Hi. Tungsten iodide, oxide iodide as well as Hi, both are the gaseous molecules. Another example is the separation of copper and cuprous oxide using HCl transporting agent. The reactions involved are cuprous oxide Cu2O, which is a solid compound, is reacted with HCl gas at 500 degrees Celsius as well as 900 degrees Celsius and change into CuCl and H2O in vapor state. And copper, which is in solid state, moreover reacted with the HCl gas at 600 degrees Celsius and 500 degrees Celsius, change into copper chloride CuCl and hydrogen gas. Since copper chloride CuCl forms exothermically from cuprous oxide and endothermically from copper and Cu2O, is actually from Cu2O is redeposited at higher temperature and copper elemental copper at lower temperature. The These examples are simple cases of transport in which reactant and products are same. For use as a preparative method, a transport is coupled with a subsequent reaction, such as at T2. If we talk about at T2, then A solid, if reacted with B gaseous, then it change into AB, which is a gaseous compound, and it may not be the reversible reaction. At T1, AB, which is a gaseous state and obtained in the first T2 reaction, reacted with the carbon in the soot form, which is actually the solid state, is actually changed into AC and B, which is a B is a gaseous state while AC is a solid state. And we will get the overall net reaction in which A solid and C solid, carbon solid, change into AC solid. There are uh, some examples that would be able to understand about the chemical vapor deposition method. In these reactions, uh, there are many other examples of using this method to prepare binary, ternary, and even quaternary compounds. Some examples uh, of the chemical vapor deposition methods are as under, and we will discuss like these examples in which the AB change into AB, while platinum solids change subsequently into platinum oxide, while chromium iodide gaseous molecule is formed by the reaction of chromium and iodine molecule. And we know that the formation of chromium iodide is exothermic in nature, and chromium metal is redeposited at higher temperatures. Other metals which may be purified by these methods are many important transition as well as lanthanide metals, in which we can see that copper, iron, titanium, neodymium, vanadium are the most common metals that can be extracted and purified by using this method, while the Mond process for the purification of nickel was very important industrial scale reactions in which nickel is reacted with the carbonyl compound at about 50 degrees Celsius and 230 degrees Celsius, and it produced the nickel carbonyl. This is quite an old industrial process for extracting high purity nickel from impure nickel obtained by reduction of nickel oxide. But this is actually falling out uh, of the favor because of the environmental issues concerning nickel contamination, and also some human health concerns over the toxicity of carbonyl and nickel carbonyl. This is all about this lecture. Thank you very much.